Hello and welcome to Quantum Mechanics Made Easy Beginner Problem Playlist. In this video, I'll solve problems related to matter waves. My name is Dr. Jacob Hudis. In the beginning problem playlist, I will solve quantum mechanics problems that don't involve pages of algebra. There will be another playlist, Mastering Quantum Mechanics Through Problems, and that will cover more complex examples. Before I start solving example problems on the next slide, I want to introduce the two fundamental important formulas. These two formulas are where quantum mechanics started. These formulas came from Einstein for light, but Louis de Broglie took these formulas and applied them to matter. And so these are the formulas for matter wave. Any particle of matter has a wavelength. If a particle has some momentum p, the momentum is equal to h bar k and it's equal to h over lambda. And that says that the wavelength of a matter wave is equal to h over p or h over mv. If the wavelength is large, the momentum is small. If the wavelength is small, the momentum gets bigger. Another formula is the energy of a particle is equal to h times its frequency. Particles have wavelengths and they have frequency, and so a particle with a larger frequency has a larger energy and a particle with a smaller frequency has a smaller energy. K is just a wave number, it's 2 pi over lambda. The probability of finding the particle is what's waving in the matter wave. So in a water wave, it's the water that's waving. In an electromagnetic wave, it's the electric and magnetic field that's waving. And in a matter wave, it's the probability of finding the particle that's waving. Here's the first example problem. If moving at 1,000 meters per second, what would be the wavelength of an electron and B, a 9,000 kilogram elephant? Which would be more likely to exhibit a wave nature? You might want to pause the video now because I'm going to go through the solution on the next slide. Hi, and here's the solution. For a matter wave, lambda is equal to h over mv. H is 6.63 times 10 to the negative 34. For an electron, the mass of an electron is 9.11 times 10 to the negative 31 kilograms. The velocity is 1,000 meters per second, and this gives a wavelength of 7.28 times 10 to the negative 7 meters. The elephant moving at 1,000 meters per second, that'd be a sight to see. The wavelength of that elephant would be h over the mass of the elephant times the same velocity as the electron, and that would be 7.37 times 10 to the negative 41 meters. This is smaller than the Planck length. So this is a very, very small wavelength. The electron is much more likely to exhibit wave nature because its wavelength is significantly larger compared to the elephant's wavelength. Please like and subscribe to the channel, and also check out my website, acephysics.org, if you're looking for math and physics tutoring. Now I will move on to a problem involving an application of matter waves. The transmission electron microscope is essential in physics and engineering and other fields. It replaces the optical microscope's light beam with a beam of electrons accelerated through a potential difference. It also uses a magnetic lens, not a glass one, but we don't need to discuss that right now. This would represent the electron being accelerated through a potential difference. There'd be a filament here. The electron would get pulled off of the filament, and then it would accelerate downward. There'd be a hole, and it would leave this hole with some velocity, and that velocity would correspond to a wavelength, and you'd use that wavelength in the microscope. You can say the potential energy at the top is equal to the kinetic energy at the bottom. This is just conservation of energy. And so QV is the potential energy of the electron, where V is the potential difference between the two plates. That has to equal to kinetic energy, 1/2 mv squared, or p squared over 2m. And then when it leaves here, it's going to have some wavelength. Will a larger potential difference lead to electrons with larger wavelengths or smaller wavelengths? What do you think the answer is? The rule you should always remember is the smaller lambda, the larger the momentum. Small lambda means big momentum, big speed. Big lambda means small momentum. Now let's move on to the next example problem involving a TEM. To obtain a good diffraction pattern, the wavelength of the incident wave should be comparable to the separation of the diffraction grating. This is for any wave, not a matter wave. In the case of an electron microscope, the diffraction grating, in quotes, is the crystal lattice spacing of the atoms in the material. If the crystal spacing is 0.2 nanometers, what potential difference would be used to accelerate the voltage of the TEM? Part B. If the TEM has a maximum accelerating potential of 50 kilovolts, how small a detail could the microscope resolve? You might want to pause the video now because I'm going to go over the solution on the next slide. To find the potential difference V, we first set up conservation of energy, and we say the potential energy equals the kinetic energy, so QV equals 1/2 mv squared. This is for the electron. Now we know V is equal to P over m, but P is h over lambda, so we can write V, the velocity of the electron, in terms of its wavelength, because this is matter waves that we're talking about here. And then we would take V, plug it in here. Well, we take V in this form, plug it in here, and this gives you a formula for voltage. And the voltage is h squared over 2mq lambda squared. H is Planck's constant, m is the mass of the electron, q is the charge of the electron, as lambda is the wavelength of the electron. Let's plug in the values. Planck's constant to the mass of an electron is 9.1 times 10 to the negative 31 kilograms. This is the charge, 1.6 times 10 to the negative 19 coulombs, and the wavelength has to be on the order of the spacing, or else you won't get diffraction. So the wavelength has to be the distance between the atoms inside of the crystal lattice, which is 0.2 times 10 to the negative 9 meters, because that was given in the problem. And that says that the voltage has to be 38 volts. For an accelerating voltage of 50 kilovolts, we're going to use the same formula, but now we're going to have to solve for lambda. So V is replaced with 50 kilovolts, H stays the same, 2, mass of the electron is the same, the charge of the electron is the same, but now we solve for lambda, and this says that lambda is equal to 0.0055 nanometers, and so in theory, that's the best resolution you can get. Hi, let's move on to the final two problems. These problems are related, and of course, they're still on matter waves. First problem. The moon orbits Earth at a radius of 3.84 times 10 to the 8th meters. For it to behave as a classical particle, its wavelength should be very small compared to the region where it's confined. Given the moon's orbit radius, compare the wavelength to this dimension. Does the moon indeed orbit as a classical particle? So here's the moon, and the moon orbits Earth at a radius of 3.84 times 10 to the 8th meters. This is the mass of Earth, this is the mass of the moon, and what we want to do is find the wavelength of the moon and compare the wavelength of the moon to the radius between the moon and the Earth. And if the wavelength is smaller, much smaller, then it will be a classical particle. If the wavelength was on the order of 3.8 times 10 to the 8th, then it would be a quantum particle, but I can tell you that's not going to be the case. You may want to pause the video because I'm going to show you the solution on the next slide. To solve this problem, you have to find the velocity of the moon, and then once you have the velocity of the moon, you find its momentum and its wavelength. To find the velocity, we say net force equals mass times acceleration. The force is the force of gravity. That's equal to the mass of the moon times the acceleration. The acceleration for circular motion is v squared over r. You can then solve this for v, and this tells you that the velocity of the moon is 1.02 times 10 to the 3 meters per second. Now that we have the velocity of the moon, we can find the wavelength of the moon. Lambda is equal to h over mv. H is standard 6.63 times 10 to the negative 4. The mass of the moon was given. We just solved for the velocity. The moon has a wavelength of 8.85 times 10 to the negative 60 meters. All right, and here's the final problem. Given an average radius of 1 nanometer for an electron's orbit in a hydrogen atom, calculate the speed of the electron and determine its wavelength. Does this imply the electron can be treated classically? And then also note that in reality, the speed would cause the electron to radiate energy and spiral into the nucleus. I hope you're aware that a hydrogen atom is a proton and an electron, so it would kind of look just like the Earth and the moon, except for not at all. Okay, and here's the solution. You solve it generally the same way we solved the previous problem. Net force equals mass times acceleration, but in this case, the force is the Coulomb force, K, 1 over 4 pi epsilon naught, Q1, Q2 over r squared. And acceleration is mv squared over r again. You can then solve for the velocity, and this says that the velocity of the electron, if it were actually a particle rotating around the nucleus, which it's not, would be 1.6 times 10 to the 6th meters per second. Now that you can take this velocity and solve for lambda, lambda is h over mv, and this tells you that lambda is 4.6 times 10 to the negative 10th meters. The wavelength is comparable to the orbit's radius, implying that the electron can't be treated classically. It's a quantum particle. It's a wave. Are you in need of a great physics tutor? Dr. Hudis can help. Whether you're preparing for a high school test, AP test, or college exam, let me help you ace it. Are you an eager high school student aiming to get ahead and prepare for college-level physics? Or maybe you're a college student and you want to learn even more advanced physics? Dr. Hudis can help. Visit acephysics.org and schedule a lesson today.